not much on the air, but
No,
dabble around a whole lot.
I did radar on radio when I was in the military,
Okay.
and then I kind of got out of it, and ventured into the medical field, but never worried to get my amateur radio license, and I rode last year. So
All right. So where do you work now?
I work for a medical company.
Okay. In electronics or?
I used to be on the technical manager for the company, but now basically I've moved into the sales management position.
All right. Boring stuff.
Let's not go there. You see my eyes roll back, you know exactly what I'm on about.
So the Space Digital Group at SKA, and we have very sort of specific requirements from our software-defined radios. The entire telescope is a software-defined radio.
I've got two of the guys there that stand for me. One guy's name is Pop.
Oh, Francois.
Francois that works with you, and the other guy, what's his name?
CS Milan.
No, not him. No, I haven't
Philip
met him.
Gibbs left.
Has Philip left?
Yeah, he's in the
Philip
UK
stays
now.
around the corner from me, or used to.
Yeah. The scientists always want as much bandwidth as they can get. So that's goal one, is to process as much bandwidth as possible. So you buy these little SDRs, maybe you got that Realtek part that you slot into a USB port and you kind of get a megahertz of bandwidth, or you buy one of the USART boards and you get maybe 50 megahertz, or like the Red Battaya or something. So this board is 3 generations old and it's doing 900 megahertz, and that's only on one input. It's got the capacity for 4, so you can do a lot more. It's just a quick demo I threw together. Our second generation board replaces 2 racks full of Intel Xeons, and now we're on to the next one. This guy can process 1 million two-way radio stations simultaneously. So kind of put it in perspective. So they're pretty beefy things. And we'd love to be able to just do this with computers, but you can't get the data into them. So we ended up having to design our own boards, and we use a lot of memory. There's a lot of memory I/O, and there's a lot of I/O ports to get the data in and out of the things.
So does, what's his name, Wesley New work with you guys as well?
Yeah, Wesley's on my team actually.
Oh, okay.
Yeah, he's folks out Nerdway. You know him through them.
Through Arduino Capton, I met
Oh,
him
right.
through
Okay,
that.
yeah. We call him Arduino King in the office.
Yeah, because I've been to your office outside, wait for Wesley to get my parts many a time before. I've kind of moved on. I still use Arduino, but I'm mostly using ARM processors now.
Yeah, no,
To get the speed.
it's all FPGA. The only time we play with embedded stuff like that is for the control and monitoring, just to manage the system. So these are Power PCs, back from the bad old days before ARM. Power PC was the business. Our new board, we've got a slightly different approach. It's got no processor units. It's just an FPGA. When you turn this thing on, the FPGA boots up off a little memory, and it runs a little soft processor. It sets up the network and so on, and you then remotely reconfigure it with the network. So it's
You load up what you want to do.
exactly. So we've saved a lot in terms of the board complexity. This entire portion of this board is just for that processor to run. So all of that stuff's now gone on the next generation part.
And these are to be put into the radio telescopes.
This one's broken.
Yeah, but I mean, you use these as your radio telescopes.
So
Do you have one per telescope?
It's actually a more difficult question than that. It turns out with radio telescopes, the processing is an n squared operation. So if you have n telescopes and you double it to 2n, you need 4 times the processing capacity you need with just n. So to build a small telescope is really easy. Cat 7 was built with these guys, and there were 16 of those boards, and it runs the whole telescope, no problem. MeerKAT is 64 antennas, and we're deploying these guys, which are 2 generations later, and we've got 300 of them in there.
So what happens to all the data? So you listen and then the data gets processed after the fact? Or?
So we do all the real-time processing on here to try and reduce the data just so that we can get them into computers.
Right, okay.
And then once they're in computers, we store it for 6 months. So there's a kind of 6-month rolling window. And we also do real-time processing on that to produce real-time images of what you're seeing. We look for transients, so pulsars and any weird things that might pop up. there are a few different things that run in real time on it as well.
Yeah.
You can always go back to the data.
Do you use different firmware for different experiments, or is it the same firmware for the whole 6 months?
So that's kind of one of the things that sets MeerKAT apart. Because these boards are reprogrammable, we can now do that. We run different firmware depending on what the scientist wants to do. And it's made MeerKAT really much more dynamic, and you can do interesting things with it. So traditionally these things would be built with custom hardware, and they'd run a particular set of firmware, and that was what the telescope could do. But MeerKAT, the entire thing is an SDR. You can software-defined radio. You can reconfigure the whole thing to do something different. So initially we'll be deploying it with a few different modes that are targeting specific types of science, but you could change it later.
Awesome. So basically it's the very simple, same principle. You've got an SDR front end, and then you've got basically your I and your Q coming out, if I'm not mistaken, and then basically your FPGA or whatever the case may be, your PowerPC does all the crunching and extracts all the info out of it. Is that the gist of it?
That's pretty much it, yeah. So it's like if you were running new radio on your laptop or whatever, just much bigger.
Been there, done that,
Yeah.
lost interest.
It's just massively parallel, and you've got FPGAs to process that amount of bandwidth.
Yeah, well that's the thing, I mean on these...
Petabytes of storage to store it for 6 months.
We do 15 terabits per second. So it's very high data rates, and there's just no way to get it into a computer, raw. So you can't bring. If we could, we'd bring IQ straight into a computer and just catch it, but we can't. So you use FPGAs for the initial processor.
And then what is the FPGA then split out?
It's an intermediate data product called UV product. It's a way of sampling the sky. So if you could imagine if you had a digital camera and you took a photo of the sky, you have like a CCD on the camera with lots of pixels, so you see all the pixels. But the way a radio telescope works is slightly different. You've got all these dishes on the ground, and what you're doing is measuring the time it takes for this common signal in the sky to reach each dish. So what you have to do is take a dish and time it against all the other ones. Take another dish, time it against all the other ones. Take another dish, time it against all the other ones. So that's where the n squared operation comes from. You have for each pair of dishes, you have to calculate the phase difference. And the thing that does that is called a correlator. And so for each pair of dishes, you get a different pixel in the sky. But because you don't have an array of these dishes that are nicely spaced and all kind of next to each other, you've subsampled the sky. And each pair is creating one pixel. Different pairs at different lengths apart to kind of pick up different points, different UV points they're called. So that's where this term UV output comes from. It's kind of a...
And then that then goes through some other processing to extract whatever that metal is.
Yeah, so then you deconvolve it with the telescope's response, which is the subsampled effect, and then you get an image popping out. So you do a 2D FFT on it, and I'll try and show some pictures tomorrow.
And so this sort of image that comes out, is that at a point where it's ready for an astronomical scientist to interpret?
Yes. So it depends on the science you're doing. In fact, there's a whole new sphere of science called non-imaging science. When radio telescopes first started being built, the guys would try and make images with it. That was the thing, take a photo. And typically, you'd often compare it to an optical telescope, and you see different things because you're looking at different wavelengths. But now there's this field called non-imaging science, where they're looking for blips, things that are changing. There's something called pulsars, binary pulsars, when they're spinning around each other like this, and every time they pass each other, there's a blip of radio spectrum that comes out at you. And we can see that, but it gets really complicated because as the signal passes through stuff in space isn't a perfect vacuum, the signals actually get delayed differently. So you end up receiving some parts of the band before other parts of the band. So in order for you to figure out what the pulse looked like when it was emitted, you have to do something called de-dispersion to fix this dispersion, this filtering that happened when it got to you, and kind of reconstruct what the original signal looked like. And you get these nice looking blips out. Anyway, so that's a big area of science at the moment. I mean, it's one of the things they're going to use to verify Einstein's theories of gravitivity.
Yeah, because that's
gravity.
And what sort of...
that's non-imaging as well, with the LIGO detecting gravitational waves.
Yeah.
And are you listening to the complete sort of 900 meg bandwidth on these radio telescopes?
In real time.
In real time.
This is Cat 7. This is
Okay.
old. MeerKAT will go up to 14 gigahertz eventually.
Is that where everybody on the